So now I spent some time talking about ISAs other than MIPS, and I pointed out to you a little confusing thing that x86, one of the most popular ISAs, is memory register, but I told you all hardware today is register, general purpose register load store machines. So what's going on here? Well, the answer is the ISA lies, but you can trust it. And let's explain what I mean by that. So the ISA gives us this simple view of the processor, and we talked about this earlier in the class. It tells us that it is atomic, that is, instructions execute one at a time, and sequential, instructions execute in the order you wrote the code. So atomic and sequential, and we talked about these both being very important so you could understand what your program does. It also gives you this illusion of a flat memory. It tells you that any memory access is going to be the same speed as every other memory access, and none of these are actually the case. So let's take a look at how the ISA is lying to you. So here's a picture of AMD's 8-core Bulldozer processor, and you can see here we've got 4 modules, 1, 2, 3, and 4, and each one of these has 2 cores. So let's zoom in on one of these cores. So here's the core from AMD's Bulldozer processor. You can see it's got a lot of stuff in it. So right here we have instruction decode and a microcoded ROM. And what this part here is doing is it's converting x86 instructions into MIPS-like instructions. So it's taking those complicated x86 instructions and it's breaking them up. So here goes that atomic thing. So the atomic thing says instructions execute one at a time, but if you write a MIPS instruction, which says load something from memory and put it in a register, or do an add to it, it's going to be broken up into multiple chunks of the instruction, which are then executed. So much for atomic. If you look down here, we've got 2 things called the integer scheduler. And what are they doing? Well, these are responsible for scheduling instructions to run out of order. So the processor here is actually looking at all the instructions you're going to run for the next amount of time and trying to figure out what can I run in a different order to make it go faster. So much for this promise of running things sequentially. Here we're doing them out of order. And if you look at all this other stuff that's going on here, this is all executing multiple instructions at the same time. So we have different ways for doing integer instructions and loads and stores and doing floating point math. So now we're definitely not sequential anymore, and we're not atomic, because now we're executing multiple instructions at the same time. So far we're definitely not keeping to what we said here when we said we'd be atomic and sequential. If you look at the rest of the core here, all of these yellow areas, these parts here are all caches. And the role of the caches is to make memory look faster than it really is, at least most of the time. So in MIPS, when you do a load, you think every load is going to be the same speed. But it turns out that depending on what data you're loading, it could be very slow or very fast. And all of this part of the core here is designed to try and make it all look fast. So we've got a whole bunch of things going on in the processor here, which are breaking these illusions, but they put everything back together in the end so that you can trust them. And this is what I mean by the ISA lies, but you can trust it. The ISA tells you what you can expect from the processor, but the processor does something totally different inside. And this is how we have x86 processors that are memory register, but really register load store inside because they change the instructions into load store instructions inside. Now before we leave this picture, I want to point out one other thing up here. That's this chunk of the chip here. This chunk of the chip here is one giant transistor whose sole purpose is to turn the power off and save energy. So this much of a core is just for turning it off to save electricity. So now I want to talk about the difference between CISC and RISC. And the difference here is about simple computations. So we talked about this simple computation here in x86, saying a memory and an addition, that we need to do a whole bunch of load and adds and stores. And there are different ways to think about how you write these instructions. So if you have an architecture that provides complex instructions, this is known as a complex instruction set computing, or CISC architecture. So the benefits of this: assembly programs are easier to write. We have these complicated instructions that do complicated stuff. The downside is the hardware gets incredibly complicated by rarely used specialized instructions, and it's very hard to write compilers that use these complicated instructions. The opposite of this are architectures that only provide primitive or simple instructions, and these are called reduced instruction set computing, or RISC. The con of RISC processors is that the compiler needs to generate lots of instructions even for simple code. So we saw how MIPS needs more instructions than x86 because x86 has these more complicated instructions. But the pro of it is that the hardware and compiler are much easier to design and optimize. And this has really won out and turned out to be really important. So everything is RISC inside today to make the hardware simpler. And we saw this with x86, how it decodes the x86 instructions into simpler MIPS-like RISC instructions inside. So let's summarize the difference between ISAs here. So the architecture is what's visible to the program about the machine. And not everything in the implementation is visible. So we talked about how the implementation may not follow the architecture. In particular, we talked about the issue of atomic execution and sequential execution and how the processor may not do that, but the ISA still promises it. The invisible stuff that's inside the chip, this is the microarchitecture, and it's really messy, but it's also a lot of fun. We're going to see some really clever things that go on inside the processors these days to make them run faster, and you're going to see it's a really neat engineering challenge. Big pieces of the ISA is the assembly language. And so we've seen these primitive instructions and how they appear to execute sequentially and atomically, but they don't necessarily do that in reality. We've talked about the different ways that we can have for ISAs, so formats and addressing modes, and we compared CISC processing, which has lots of complicated instructions, and RISC processing, which only has a few. And the benefit of CISC is it's easier to write assembly language programming with fewer instructions, but with RISC it's easier to compile, but you have more instructions. So, and I want to emphasize this point, all recent machines are RISC inside, but x86 is still CISC. And the way they get away with this is they convert their CISC instructions into RISC on the inside. So question, what are all processors internally today, and why? Well, today all the processors are RISC inside because it's easier to build the hardware. They're really, really complicated, and building hardware that handles specialized instructions is really tricky. So what x86 processors do is they decode their complex instructions into RISC micro operations, and then they run internally as a RISC processor. Intel claims this takes about 2% of the chip to do this decoding today. So which of the following things here does the processor do internally? Well, internally it converts all instructions to make them easier to process. So we talked about how the x86 processor can convert them into MIPS-like RISC instructions for processing. We also talked about how we don't access all memory equally fast. We talked about how instructions don't execute atomically. They get split up into smaller instructions and they get executed multiple at the same time. And how they don't execute in order. We try and find the right order to do them in to run it faster.